Okay, so welcome back. A couple of days back, I had the pleasure of introducing an old BTech student, Ashoka. Today, I'm introducing a former PhD student. Shalabh started with physics in Delhi University, then did his master's and PhD in Ministry of Science. After a couple of years in University of Maryland as a postdoc, he rejoined ISC and has been there ever since. He works in started out in simulation optimization, which he still revisits once in a while, and also doing stochastic approximation theory and reinforcement learning. And unlike me, he does useful things. He does a lot of interacts a lot with government and industry and so on. And the Bangalore traffic, you see, would have been much worse without him. He has done a lot of work for the Bangalore transportation.
Yeah, comes. Yeah, thank you all. It's a pleasure to be here, and thanks to the organizers. And thanks to Professor Borkar for that more than generous introduction. Actually, there is nothing I did for the Bangalore traffic. It's all in papers. Nothing implemented on the road as such. Okay, so today I'm going to be talking about n-step temporal difference learning. So there is, and with an optimal n, and we'll see what that optimal n is. So this fits into the setting of reinforcement learning in general. So here is some key takeaways. So what I'm going to talk about is essentially this paper on with my PhD student who is now going to defend a thesis, Lakshmi Mandal. And this has appeared recently in Automatica. What we are going to talk about is essentially some interplay between a lot of things. So start off with reinforcement learning. So essentially TD learning is what we call as an algorithm for the problem of prediction. The idea is if you have a certain given policy, you want to estimate the value of that policy and you don't know the system model. And TD learning helps in that regard. And it's an incremental update algorithm for this problem of prediction. So which means you just want to understand the value of that policy without really bothering about what the optimal policy is. N-step TD learning kind of extends that idea. It sort of balances between Monte Carlo. Monte Carlo is like fully trajectory-based methods. So whenever, let's say you are in a certain state, you pick an action, and we'll come to some of these basics later. You get a reward, but then you sort of accumulate reward over the entire trajectory. And once you have that, then you sort of try to make sense of it or take the expected value of those rewards and so on. And which essentially can be a tedious process, particularly if the number of states is large, the visitation instants are quite infrequent and so on of the particular state, which we call as the goal state and so on. So TD methods are the other extreme. They update as soon as you have a data tuple, or a sample of data that is available. N-step is kind of balancing between. Okay, so it's sort of, there is this whole spectrum of approaches that are possible between one-step temporal difference learning and fully Monte Carlo. So N-step is a deterministic N. You sort of try and fix that N, and then there's this entire all these possibilities exist. I mean, you can select any N and work with that. Here is an important observation, however, that even though if you use n-step TD for any N, use the algorithm that you obtain converges to the value function that you desire. But different N values result in different root mean squared errors. And this is an observation that is made in the textbook by Richard Sutton and Andrew Barto. I think it is in chapter 7 of their book. They actually did a lot of experiments with different N, and then they show that the root mean squared error is different for different values of N. And that gave us the idea that, well, why don't we try and figure out what is that optimal N? Okay, so that tries to minimize the root mean squared error. That was the genesis of this problem. That was chapter 7 of Sutton's book. So the question that we address here is how do we adaptively select N in an n-step TD algorithm? And the algorithm we use is a bit complicated. I'll tell you what it does. But it is a discrete version of what we call a simultaneous perturbation stochastic approximation with an n-step TD update in between. The main results that we have, essentially what we do is to prove almost sure convergence. So the resulting scheme is a 2-time scale stochastic approximation, and then we need to use some sort of differential inclusions-based analysis. And we show that it experimentally does better than this OCBA procedure, which stands for optimal computing budget allocation. This is actually a well-known discrete optimization procedure. So here's sort of a summary of what I'm going to be talking about. I'll start with a very brief introduction to Markov decision process in RL, just to put things in perspective. Then I'll talk about the prediction problem and basically Monte Carlo approaches. And then a very short summary of, maybe a 2-slide primer on stochastic approximation and model-free approaches. Then I'll have another 2 slides on stochastic approximation and SPSA and the tweak that we have of one simulation SPSA with a cyclic cancellation of bias terms. Then I'll talk about TD learning and step TD, and then we need these discrete random projections because SPSA by itself is a continuous optimization scheme. But then now here we are optimizing n, so n is discrete, right? N is 1, 2, 3, and so on. So how do we need some sort of a projection to that space of the discrete space based on whatever continuous values the algorithm is sending us. And then I'll talk about a little bit of how do we analyze these schemes and then some experiments. So let's assume that we have a Markov decision process, and by an MDP or a Markov decision process, what we mean typically is a sequence of random variables, let's say xn. These are all defined on a common probability space, but then they take values in a certain set S, and that we call as a state space. And the evolution of this sequence depends on another control valued process. Let's call it a sequence Zn. Sequence Zn, all these Zn's take values in some set A. In fact, they may take values in subsets of A, depending on what the state is. And they satisfy what we call as the controlled Markov property, which is on the next slide. We'll assume in this talk that both of these sets, S and A, are finite sets. And the important thing is that whenever you are in a certain state, you take a certain action from this set, and you move into another state, you incur a cost. Okay, so this is the cost that you incur by choosing this action in this state, and when the next state is this. So the controlled Markov property is essentially what it says is that if you are already in state S at time n, you decide to take action A at that instant, depending on the state. And then if you put this entire history of evolution of the current state action and so on until then this whole thing, the future evolution, which is the evolution at time n+1, only depends on these two entities. It does not depend on how you actually arrived. And that's what this figure is trying to explain. You may have taken different paths, but as long as at time n you are in Sn, you take action A, and the future evolution does not really depend on how you arrived. So this is one of the sort of an objective criterion, and this is what we use in this in here. So the idea is that we wish to find a sequence of controls, sequence Zn, that minimizes the value function. And the value function is defined in this manner that given any initial state I, so there is this conditioned on x0 is I, you want to look at the expected sum of these discounted costs. Okay? So gamma is a discount factor that takes values between 0 and 1, but less than 1. And V star I would be the minimum over all such sequences of Zn, of V Zn of I. And then there's this defining sort of an equation that we refer to as the Bellman equation. What it says is that the optimal cost function satisfies this equation. What it says is that if you look at the value of state I, we refer to this as the value function of the, if you put in V star of I, it is the value of state I or the optimal value of state I. So the optimal value of state I is the minimum over all possible actions of the sum of the expected single stage cost plus discount factor times the value of the next state. So that's essentially what the Bellman equation says, but what is also important is that this quantity V star that you obtain is a unique solution to this equation within the class of bounded functions. The prediction problem is simpler. So if you can largely break down RL problems into two broad categories. One is what we call as a problem of prediction, and then there's this problem of control. The problem of prediction essentially says that given a policy, I want to estimate the value of that policy. The problem of control is I wish to find an optimal policy, okay, and which will then take in this problem of prediction as kind of probably a subroutine. So whenever you update your policy, you call this subroutine to estimate what that value of that policy is, and then you update your policy again. So there's some procedure that can move in along those lines as well. So the problem we tackle here is the simpler problem. It's just the prediction problem, which essentially says that given a policy pi, again, by a policy, we mean this sequence of functions. Let's call them pi 0, pi 1, pi 2, and so on. Each one of these functions is a mapping from the state space to the action space. And we are assuming here that, of course, all actions are feasible in every state. And so otherwise, you will have to restrict your attention only to actions that are feasible, okay, in any given state. And a stationary policy pi is one where all of these functions are the same. I mean, pi I, pi j, they are all the same. Let's call them as pi. Okay. So the prediction problem is given a policy by a policy, then now I mean a stationary policy. So by a stage so if you are given a policy pi, you wish to find the value v pi of s. And this should be s or this should be I. I mean, there's a typo here. Let's call it as I. So v pi of I is this expected value. So I wish to find the value of this state I. Okay, so that's the problem. Now, corresponding to this policy pi, we have another Bellman equation, which essentially is just over policy pi. Okay. So which essentially means there is no min here. Or alternatively, you think of a problem where for every state I, there's only one action that is feasible, which corresponds to this policy pi. If it is a stationary, what we call as a deterministic policy. Many times we also refer to this as a deterministic policy. So then there's only one action possible, and then the same Bellman equation as was described will give you this. Essentially, that's a way of deriving this from the earlier one. The reinforcement learning setting is essentially borrows a lot from the usual Markov decision process setting. And what it says is that, well, there's this agent that is interacting with this stochastic dynamic environment. The environment can be in one of these several states. And the agent at any time looks at the state of the environment. Let's say it looks at the state Sn, picks an action, and then the environment moves probabilistically to another state, let's say Sn plus 1 at time n plus 1, and gives the agent a reward. Okay, so there's a reward that it obtains. Yeah, in reinforcement learning, usually there is this notion of rewards as opposed to costs. Okay, so yeah, so that's, but it's analogous. I mean, there's no change really in the way these problems are solved. So then the agent again picks another action, the state moves to another state, the agent gets a reward, and this process repeats. So the goal of the agent is to figure out a sequence of actions in response to the states of this environment in order to maximize a certain long-term reward. Our long-term reward is a discounted reward that I just mentioned earlier. The problem now is we don't have access to transition probabilities. With what probability this moved from Sn to Sn plus 1 is something that is not known. But what we have is that instead of probabilities, we are actually observing. So we are observing states, we are observing, anyway, we are taking actions as a decision maker, so we know what action has been chosen. Then we are observing the next state, we are also observing this reward signal. So this data is available to us. So what Monte Carlo schemes typically do is they look at this. So this is your objective. This is the objective function. And you want to find what this objective function is. So usually Monte Carlo estimates, what they do is they would run multiple episodes of with policy pi, starting from some initial state. And then you take these actions according to pi, you get these rewards. And then, so if there's this initial state, you take this initial action, you get a reward, you get to the next state, and then you take another action, and keep doing this. And if it is an episodic problem, which essentially means that you terminate in a certain goal state or a terminal state, then the trajectory ends of its own, okay, once you hit that goal state. Now let's assume that, and so you run multiple episodes and you collect all of this data. Let's say your state I is visited a total of n times. Then what you do is, let's say we calculate this return on a trajectory. It's essentially something like this. So it's just that it's being computed on a trajectory and there's no expectation, because there's just these rewards that you are looking at, and then you are aggregating over all of them. Okay, so the Monte Carlo estimate will just be an average over all of these returns that you obtain. As mentioned here, the problem with Monte Carlo is you cannot start updates until and unless the whole episode of data is available. Unless that is done, then unless that happens, you cannot really update. So that is where we appeal to stochastic approximation. This started out as an area via this seminal paper of Robbins and Munro, which appeared in 1951. So what they said was, if you wish to solve an equation of this type, g of theta is 0, and you really don't know what the analytical form of j is, but what you have is, let's say you have access to noisy measurements of j of theta, which means if you input theta in this box, you don't observe j of theta, but you observe a noise corrupted. You have this noise corrupted measurement. Let's call it as j theta plus this noise. And what Robbins and Munro did was to solve this equation. What they said was, there's a way in which you can update theta. So what they say is that, well, you start off with some initial guess of theta. Let's call that theta naught. And then as long as you have these observations that are available, you keep passing theta as it gets updated through this box, and keep making these observations, which you plug in here and multiply with what we call as a learning rate or a step size. And then you add it to the previous value of theta to get a new theta. And once you keep doing this over a period of time under certain conditions, you can actually show that theta n will converge to some theta star, let's say. That theta star will be such that this is actually met, which means j of theta star is 0. The advantage with this algorithm is, nowhere in the process are you really trying to estimate the form of this function j. When you have this algorithm wherein you just make use of these noisy measurements, you know that upon convergence, it will converge. It will give you a theta for which j of theta is 0. Well, their algorithm was in a less general setting. I mean, the analysis was in a less general setting. So they made some assumptions on, let's say, the noise is IID and so on, which over a period of time has been relaxed. And now this is what I am referring to. This is book of Vivek Borkar. The first edition appeared in 2008, and then the more recent edition with a lot of new stuff has appeared in 2022. I think that there's also a Springer version of this in 23. And what is mentioned here is that, well, if you look at typical applications of stochastic approximation, this could be in finding noisy fixed point computations. Let's say you wish to find a theta star for which f of theta star is theta star, but it's just that you don't know what f is. But you have access to noisy samples of this function f. In such a case, you can rewrite j of theta as f theta minus theta, and then the problem reduces to finding a 0 of j of theta. Okay. Or a noisy gradient scheme wherein, let's say, you don't know, you wish to find the local minimum of this function f. Again, you don't know what this f is, but you have noisy estimates of f. And then you set j theta to be minus grad f of theta. And then as long as you have some noisy estimates of this minus grad f, that you are fine. I mean, you can apply this scheme. So here's the general result. What it says is that, well, suppose you have a function j, your function j is Lipschitz continuous, and your step size sequences of the learning rate parameters satisfy these two conditions. This condition essentially tells us that the sequence of the partial sums sort of diverge of these step size parameters, but they are square summable. The square summability essentially ensures that the noise and the discretization errors and so on, they vanish in the asymptotic limit. As far as the noise is concerned, we assume for now that it is a martingale difference sequence with respect to this sequence of some sigma algebras, script fn. where sigma algebra script Fn is essentially this sigma field generated by theta m less than or equal to n. So you have this sequence of all these observation sigma algebras obtained from all of these this entire history that is available to you. We make this additional assumption, which says that if you look at the expected value of the norm mn plus 1 square conditioned on Fn, that is upper bounded by some constant k into 1 plus norm theta n square. This assumption is of course non-trivial. It says that supremum over n norm theta n is finite almost surely, which essentially ensures that the iterates are uniformly bounded with probability 1. It's just that the bound on the iterates is not constant across sample paths. On different sample paths, you will have different constants. Essentially, that's what is a requirement. And there are general conditions, there are sufficient conditions under which one can actually show that this condition will hold. But of course, one needs to verify whether or not that happens. In situations where you really are unable to verify this, and a commonly used procedure is to sort of project iterates to a large enough set, a priori defined. Let's say it's a compact set, and then you solve a restricted problem wherein every time it escapes that set, the iterate sequence escapes the set, you project it back to that set and start from there. So the theorem essentially, what it says is that it's available, it's from this paper by Michel Benem, also available in Borkar's book. What it says is if you have all of these conditions holding, then theta n converges to A almost surely, where A is a sample path dependent compact connected internally chain recurrent set of this ODE. This H is essentially, oh sorry, this should be J, not H. Yeah, there's a typo again. Sorry about that. Yeah, so we'll now move towards another problem, and this problem is on stochastic optimization. So let's say I have an objective function J, and it's a mapping from R power n to R. And let's say this is a given objective function having a form like this. J of x is a parameter, x is an n-dimensional parameter. So J of x is expected value over mu of h of x mu. So mu denotes some noise terms, d mu is the expectation under that noise. So what this figure shows is that, well, on different sample trajectories for different values of the noise sequence, you have different paths that are emerging. And what you are interested in doing is to look at this solid line, which is the expected value over all of these. So for any given x, you look at the expectation and you get that point. And in that manner, suppose you draw this. And then the objective is that you wish to find an x star that minimizes over all x, j of x. But again, finding this objective is tedious. I mean, one would normally have, I mean, if you can avoid it, that's actually good. So what we do is, I mean, there's a whole class of approaches that go under the name of, that go for these stochastic optimization based approaches. The classical approaches are those that use one simulation, and they then do some, so I mean, these approaches have become famous under the name of perturbation analysis based approaches. And what they do is they look at sample performance gradients. Okay, so if you say the following, let's say the gradient of j of x, which is the gradient of the expected value of h of x mu. But let's assume you are able to interchange the gradient and this expectation, which means you are able to push this gradient inside. Then it will be the expectation of this gradient of h of x mu. Assuming, of course, that h of x mu has sufficient regularity, the gradient is continuous and all of that. Okay, it's not just differentiable. I mean, the gradient is continuous over mu over. I mean, sorry, this should be x and not mu. Is grad of x, right? I mean, so for any mu, it is continuous and all of that. And there are other conditions as well. So if that holds, then you can really work with these sample gradient estimates and plug them in your stochastic approximation algorithm. And upon convergence, you will see that you get the behavior. Essentially, it will converge to, let's say, a local minimum of the objective function j. Many times this is not possible. I mean, you don't have such regularity conditions holding on your sample objective and so on. And that is where zeroth order approximation methods actually help us. The first such approach was due to Kiefer and Wolfowitz. This appeared in 1952, right after, a year after the Robbins-Monroe algorithm came. And it actually suggests a finite difference stochastic approximation scheme wherein if you have an n-dimensional parameter, you sort of require 2n samples of the gradient. I mean, 2n samples of the objective function, and then you estimate the gradient based on those. Over a period of time, then there has been a lot of work on random perturbation approaches. SPSA is what we refer to as simultaneous perturbation stochastic approximation, is one such. It's, I think I have references on SPSA on the other slide. So this was due to James Pal. Okay, so what he suggested was that if you just look at one or two simulations of these perturbation vectors, wherein let's say one or two simulations of your parameter where the parameter really is a perturbed quantity. And the perturbation has a certain distribution. Let's say it is a symmetric Bernoulli kind of. So every component is perturbed with +1 with probability half, -1 with probability half. And one or two simulations is enough. This idea was extended. I mean, actually, I think the smoothed functional or SF approaches came earlier than SPSA. I think this came around 1970, in the early 70s. What they said was this was due to Katkovnik and Kulchitsky in the beginning. And later, I think they are available in books by Rubinstein and so on. So what they say is that, well, you just run maybe instead of, and Bernoulli is what Spal did, and this paper appeared in 91. Okay, so what Kulchitsky and Katkovnik said was you perturb using Gaussian perturbations. And then Rubinstein also suggested you could use Cauchy or maybe uniform, let's say uniform on a symmetric interval. All of those work, and that also became well known as RDSA, random direction stochastic approximation, which essentially looks at the let's say an open sphere, sorry, a sphere, and then you have a uniform distribution on that sphere. Okay, instead of usually one would imagine a hyperrectangle, but then it's on the sphere, and that's essentially analogous to a Gaussian. And this is available in the Kushner and Clark book of on stochastic approximation. I think appeared in 1977. It turns out that wherever you are able to do direct gradient estimations, they perform very well. And they are in fact the best methods, but many times they are not even applicable. Okay, so there is this reason why we should look at zeroth order gradient schemes. So here I'll explain the SPSA estimate. Essentially, this is due to these two papers by Spal. In the Spal, the original paper, he talks about this two simulation SPSA estimate. The later paper is on one simulation. So what the idea here is that let's suppose delta n is a vector of n, capital N random variables. And they are all IID. Each one of these delta i's is IID ±1, symmetric Bernoulli, okay, which means they take +1 with probability half, -1 with probability half. And then what you do is you run two simulations, one with theta n plus delta n. Small delta is some sensitivity parameter. Let's say you take it as a constant. And then the other with theta n minus delta n. And you obtain this objective. The gradient of this objective is estimated in this manner. Okay, and then the one simulation estimate just takes into account this parameter, removes the other one, and then this is the estimate of the gradient. You might wonder why these should be estimates of the gradient. So the idea is that if you do a Taylor's expansion of this quantity, the two simulation estimator actually gives you the ith partial derivative, and that's why this is this delta I n sitting in the denominator that helps to get this. Okay, I mean the gradient along the ith direction plus small o of delta. But if you look at the one simulation estimator, you get this quantity again, but then this capital O of delta. But there is these additional bias terms that result. Okay, there is this bias term which has this small delta term in the denominator, and this can, even though this is the expected value is 0, as you run the algorithm, this can actually increase the variance significantly, and that's what happens typically. So because of this, what we did, I mean, this is some old work. What we did was to look at essentially, particularly for the one simulation SPSA, it is more desirable that the bias terms that result, they cancel out more frequently. Otherwise, as I said, the variance starts blowing up. So in some of the work that we did, what we proposed was you sort of do it cyclically. So let's say instead of saying every time for every component you have +1 with probability half, -1 with probability half, then the next time you again come, you have to select that component. You look at +1 with probability half, -1 with probability half. Instead of that, suppose you say first time I'll take +1, next time -1, then I go back +1, -1. You alternate in that manner. You can see that there's a regular cancellation of the bias terms. Okay, and that essentially improves the performance. There's a plot from that paper. Essentially, I'm not describing the setup, but just the plot. What the plot shows is that if you use the usual SPSI with one simulation, this is what it is. I mean, in terms of the distance from the optimum. But if you improve, essentially the best you can do is something like this. I mean, so wherein you sort of cyclically cancel it using the shortest cycle length. And this is a general construction based on what we call as Hadamard matrices, matrix-based construction. This was lexicographic construction, which takes a longer time. So it's obvious that it will take a longer time for cancellation, and so the performance is not as good as Hadamard. Okay, let's get back to the temporal difference part of it. So again, recall that this is the Bellman equation for a given policy. And what we wish to do is to first write down the n-step TD algorithm corresponding to this Bellman equation. So let's say we do that. So TD essentially performs incremental updates using stochastic approximation. So let's say Vn is this vector. So 1, 2 up to mod S is so they correspond to the states, let's say. So there's a vector of a mod S dimensional vector. Let's say Sn is the state that is visited at time n. So TD algorithm is essentially what it does is in the lookup table case is essentially tries to track this equation. So this is essentially what is Sn. Sn is the state visited at time n. So we are actually implementing an asynchronous update algorithm. So you only update components of the value function that are or the states that are visited at that particular instant. So state Sn is visited at time n. So if that particular component of the value function gets updated, all other components stay the same as before. Whatever their earlier values was, you carry them forward. So in n-step TD learning, so if you look at n-step Bellman equation, the idea is that, well, what does the Bellman equation say? The Bellman equation tells us that you look at the sum of the single stage reward and then discount factor times the value of the next state. So instead of that, I mean, suppose I say I can go 2 steps, look at the sum of the 2 stage rewards and then the value from the second stage onwards. Or I can go n steps and then I stay value of from the n plus first stage onwards. All of these are valid forms of the Bellman equation. So the n-step Bellman equation would look something like this. So n-step TD can be viewed then as a bridge between TD and Monte Carlo. Let's say we define, suppose V hat n of Sk as this quantity. The idea is you look at the sum of these n-step rewards, provided this n does not occur before the terminal instant occurs. If that happens, then you only count up to the terminal instant and stop there. If it occurs before the terminal instant, then you also add this quantity, right? I mean, what happens to the stage, or what happens to the state, let's say n instants later, and then the value as approximation from then and on. Okay, so V hat n of Sk will then be V hat n of Sk plus the old value plus gamma power n times this. Okay. So this is what V hat n of Sk is. And then the TD and n-step TD algorithm would just be this. Okay, you apply this V hat n of Sk here and then update in this way. Now again, I mean, so this is an experiment. Essentially what it shows is that on a certain setting, I think this random walks example that is there in Sutton's book, what one can see is that if you change, suppose I don't assume a diminishing step size. Let's say I take a constant step size and these are the values of these constants, say 0.2, 0.4 or 0.6. Let's say this is the 0.2 case. This is 0.4, this is 0.6. Now, if you look at the root mean squared error for any of these values of n, this is how it looks. which essentially means that there are points where the root mean squared error is minimized for any given step size. Right? It's not the same across step sizes, across all of these n values for any given step size. So our objective then is to figure out what that n is that would minimize this root mean squared error. Let's say this is the sample objective, which is Gn of Si defined in this manner. Is the norm, the square difference between V hat n of Si and Vn of Si square. And then our objective is to figure out an n star that minimizes the long run average mean squared error. So let's, the values of n, the values that n can take are typically 1, 2 up to n, 1, 2 up to L for some L. What we do is we resort to a stochastic, a continuous stochastic, continuous optimization setting in the beginning, and then we sort of project it to the discrete set. So let's say we denote by d bar, which is closed interval 1 to L as the closed convex hull of this discrete parameter set D. And gamma bar would be the projection to this set 1 to L, okay, to this interval. Right? I mean, so the nth update will then proceed in this space d bar, but the actual values that you take would essentially be decided by another projection operator. And this is the projection operator. So what it says is that, well, if your update at any point in time is showing, let's say 3.6, let's whatever, and the values you are allowed are 3, 4, 5, 6, and so on, then the probability may be 0.4, you project it to 4, and the probability 0.6, you project it to 3. So that's what this random projection thing does, essentially. So then basically V hat n of x can be represented in this manner. It is a convex combination of some V hat k of x and 1 minus beta. So beta times this plus 1 minus beta times the next interval. Okay, the next parameter, which is k plus 1. Okay, so you take a convex combination of the value estimate at parameter k and the value estimate at parameter k plus 1, and that's something like this. We assume these conditions on the step sizes. So the step size, they follow these conditions that they are positive, that they sum to infinity, and then they are square summable. So these are usual Robbins-Monroe conditions. We require an addition that ak plus 1 by ak goes to z1 as k goes to infinity, which is of course satisfied by usual step size conditions. Normally, let it be 1 over k power alpha or whatever, for any alpha lying between 0.5 and 1, more than 0.5, or even log k by k and so on. All of those will satisfy this. But in addition, this is the crucial requirement. It requires that the step size AM goes to 0 at a rate faster than BM does, and which essentially means that the recursion that is run according to the step size AM is the slower recursion. It does not, while the BM recursion is kind of, you can view it as a faster recursion. And the perturbation sequence, we do it is in the following manner, that you take the value +1 on even iterations and -1 on odd iterations. And these are then the update equations. So this is the usual n-step TD algorithm for a given n. And then this is doing the finding the root mean squared, the mean squared error. And this is updating the value of n. Okay, so so this is being done on a slower time scale. You update the value of n, the n parameter, by using some sort of a gradient estimate here. And where yn plus 1 is an estimate of the mean squared error, which is getting updated on this recursion. And for that given m, you are sort of updating the value function. You're trying to estimate what the n-step TD algorithm for that is. The only catch is that this is, so nm plus is what is being used, which essentially means nm plus delta delta m. You look at the projection of this, right? I mean, so this is what you need to work with. And upon convergence, of course, we will see that this will converge to a local minimum. Yeah, this indicator SMI essentially indicates that even though all of these components are getting updated at every time, is really the component that is the state that is visited, only that particular component of the value function gets updated. All other state components for the values, all other value function components for the state are sort of stay the same. I mean, if that particular state is not visited. So what we observe is that J of n that we obtain, this particular J of n, which is this long run average of the mean squared error. This is Lipschitz continuous in this closed convex hull. Moreover, this derivative is piecewise Lipschitz continuous on intervals of this type, k to k plus 1, but open on k plus 1. But on these points, it actually ends up being discontinuous. Okay, and the points of discontinuity are sitting in the discrete set. And we obtain in particular something like this, that if you look at the derivative djn by dn, evaluated at n equals m, and take the difference with djn by dn evaluated at n equals l, is upper bounded by k1 into m minus l. So which means it is Lipschitz, but on this interval. But if you take the limit, if you come from the right, limit as n goes down to k, djn by dn, and if you go up, go from the left, they are not the same. Okay, which means there is a problem at these points. If there was no problem, if this limit was equal, then one could have appealed to maybe an ODE-based method. But because of this discontinuity, one needs to look at an inclusion, essentially. So as far as the faster time scale is concerned, if you look at the corresponding set of ODEs, this is what it is. I mean, so the ODE, the recursion on the faster time scale, on the slower time scale does not appear to move because of the fact that you can rewrite this as Bm into Am by Bm into this. And delta is a constant for us. So you can see that because Am by Bm goes to 0, along the faster time scale, this is the sequence of ODEs. There's a set of ODEs that you obtain. Okay, but because of the fact that n dot t is 0, essentially you can rewrite these equations in this manner. And one thing is, if you look at this ODE is 8. So y star is j of gamma bar n plus delta delta m will turn out to be its unique globally asymptotically stable equilibrium. And yeah, so what this ODE essentially is what it is. Here D is actually, what is D? D is actually the, look at it as a diagonal matrix where the diagonal terms are all the stationary distributions of the Markov chain that results under this policy pi. So here is this proposition as far as the faster time scale recursions are concerned. We obtain the convergence of this type. And it's just straightforward. I mean, there's not much of a difficulty in arguing this. The problem arises with a slower recursion because of the discontinuity, as I mentioned. So if you look at the OD, just the OD, the OD would be something like this. If you don't go into the asymptotic limit, you will get an OD, and that OD will be this. The problem arises if you try to push this delta towards 0. And then this would be the OD. The problem is this is discontinuous. Okay, it's Lipschitz continuous on intervals, but on the boundary points it is discontinuous, and that's the problem. So that is why we need to resort to a corresponding set valued map. So we look at this set valued map. Let's say h of n is the intersection over all eta. Eta is this of these quantities. I mean, so you look at the projected value of whatever minus j dot m can be. Now, where m lies between, m is in an eta neighborhood of n. You take the closed convex hull of all of these points that are there, and then take the intersection. Intersection is over eta. Okay, so you take the intersection over all eta greater than 0. So essentially that's what you get. Now for n that are in this open interval, you see that Hn will actually correspond to minus j dot n, which is well defined. But when n is on the boundary, then there is a problem. Okay, you sort of look, I mean, then what you get is this interval, the closed interval alpha k, beta k, where alpha k is the lower limit of j dot n at n equals k, beta k ends up being the upper limit. That's essentially where we are. So we need some conditions on the set valued map. So let's say, so there are some definitions that I'll talk about now. So let's say we look at a set valued map which takes in as an input any n, it's an n-dimensional input, and in return you get a subset of R power m, subset in the m-dimensional space. So give me any point x and I get a subset in this space m. So such a map, we'll call it as a Marchand map. If these three properties hold, the first is that h of x, for any x, h of x should be convex and compact. And then if you look at supremum of norm w, where w sits in h of x, that should be upper bounded by some k into 1 plus norm x for any x. And then this set valued map H is as upper semi-continuous, which means that if you are given a sequence Xn, subset of Rn, and a sequence Yn subset of Rn, but these points Yn, Y1, Y2, and so on are such that Y1 sits in H of X1, Y2 sits in H of X2, and so on. And let's say this sequence also converges to some Y. Then if this Y sits in H of X, then we say that this set valued map is upper semi-continuous. So we say that this, if these three properties hold, then H is Marshall. Why do we need Marshall? Well, if you have Marshall, well, we are able to show that our set valued map H of n is Marshall. So if you consider then the corresponding differential inclusion of the in place of the ODE, which is n dot t is H belongs to H of nt, then every solution to this differential inclusion is absolutely continuous. And there's a result in this book by Aubin and Selina, which shows that. Some more definitions. So let's say M is a subset of R power D. We call this subset as invariant. If we start anywhere in this subset and suppose X is any point, we pick any point X inside M, then there exists an entire trajectory of this differential inclusion such that the whole trajectory sits inside M, starting from X. So in that case, we say that M is invariant. These notions sort of carry over from the ODE case. It's just that in the ODE case, for any given initial condition, you have an entirely unique trajectory if your right-hand side of the ODE is Lipschitz continuous and so on. Here, there's a problem because now you have multiple trajectories that are coming. Okay, there's some more definition. So we say that capital A has a subset of RD is attracting if it is compact, and moreover, there's a neighborhood U around A, such that for any epsilon, there exists a time instant T epsilon, such that if you see what happens T epsilon instants later and beyond, any trajectory that starts within this neighborhood U sits in an epsilon neighborhood around A, okay, and does not go beyond it, does not leave that set in epsilon of A. If that happens, then we say A is an attracting set. And in addition, if A is invariant, then we call it an attractor. There's some more definition of what we call as an internally chained transitive set. So let's say we have these solutions, let's say x1 to xn of the differential inclusion. Let's say A is your set. We say that A is internally chained transitive if the following things hold. That you pick, let's say any 2 points, x and y, x is here, y is here. But it's the same set that is moving, has been shown to move in time. Suppose now you start in an epsilon neighborhood of your differential inclusion in an epsilon neighborhood of x. And let's say you go at least some t instants later, right? And t instants later, you are somewhere here. And the differential inclusion trajectory gives you this. And you start another trajectory, let's say in an epsilon neighborhood of this, and keep repeating. Then after n steps later, let's say wherever you are, let's say, if you are able to show that this is then in an epsilon neighborhood of y. So x and y were given to begin with. If that happens, then we say that maybe you can call y to be reachable from x. Okay, so via these solutions, via this system of solutions for di. So then x1, x2 up to xn is called an epsilon t chain in A from x to y. And this set A is internally chain transitive if it is compact, and moreover, for any xy, you are able to show that this holds, that y is reachable from x. So the main result is the following, that if, so we show that nm converges to p almost surely. As m goes to infinity, where p is an internally chained transitive set of this differential inclusion 13. So this differential inclusion 13 is really this. N dot t belongs to h of nt. Yeah, the key idea is essentially you rewrite this equation in this manner, where Znm will belong to h of nm. Znm is actually j dot nm, because hnm is j dot nm in this open interval. And otherwise on the boundary points, there's these closed intervals that are there, alpha k to beta k. Yeah, I mean, it's, yeah, so there's this result again, I am appealing to this result from Benheim's paper. And what it says is that if y dot is any bounded perturbed solution to the di, then if you look at the limit set, which is L of y, which is intersection over all t, non-negative, of the closed of the closure of these sets, a set of y such that s greater than or equal to t, and this set L of y is also internally chain transitive. It turns out that the trajectory by itself is a bounded perturbation, bounded and perturbed solution to this di, and one can argue that the trajectory that you obtain of what we have, our stochastic recursion by itself ends up being a bounded perturbed solution to the di, and therefore the convergence happens. Yeah, one important interesting thing is that if j gamma, I mean the projection of this minus j dot n star, I mean we look at this the gamma bar hat of this quantity being 0 for some n star. Essentially, so if this holds, then 0 will belong to h of n star, and the recursion will converge to the largest chain transitive invariant set that is contained inside C. I mean, these are again standard results. Well, let me shift focus and then come to some numerical experiments. So what we do is we look at some experiments on one is the random walk on maybe a 21 states. And this is again given in this Sutton and Bartow's book. Then we talk about a grid world experiment involving 256 states. What we did was multiple experiments was done for different initial conditions, step sizes and so on. So here are some plots. So this is, I think, on the random walk experiment. So this is a plot of value of n versus the number of training iterations. Then, yeah, so here in both of these plots that are shown, alpha is 0.4, which is a step size, and it's a constant step size that has been used here. And then what we see is that, well, if you start, let's say with an initial condition of 16, then it settles into n star is 4 so that is where the root mean squared error is minimized. In fact, that's what the root mean squared error plot is also showing, that it's minimized at this value. And if on the other hand, you change your initial condition, let's say instead of starting from 16, you start from 2, then it jumps up to 4 and then stays there. The root mean squared error plot is this, which essentially means that regardless of the initial condition, it's sort of getting into that optimal. Yeah, I mean, that's what this is showing. We also compared the performance of this algorithm with this procedure called the optimal computing budget allocation, which is considered to be an excellent procedure. And this was published in a paper in 2010. I think there's a book actually, and there are also papers around it. And what it is actually a ranking and selection based procedure. So what you do is you try to estimate the objective function for every single value of the parameter. Now the procedure works in the following manner, that you assign some computing budget and say that, well, for that particular computing budget, I want to judiciously allocate that budget to these various competing alternatives. And then what you do is you sort of assign a small budget initially for exploration across parameters. And over multiple stages, you then sort of narrow down your search to parameters that appear more interesting. And you assign more and more budget to those estimates, and then ultimately that converges. So we adopt this procedure here. It's just that the value function is still getting estimated on that time scale of alpha for any given n. But then amongst n, you sort of update you sort of figure out what this optimal computing budget allocation gives. And here are some plots essentially. So for different, the red plots are what OCBA gives us. The green plots are our algorithm. The root mean squared error as a function of total budget for different values of alpha is seen to be consistently better using our proposed approach as opposed to the optimal computing budget allocation. In terms of numbers is how it stands. I mean, the time taken for these various values of alpha is again better in our case, and the root mean squared error is also better. Okay, so to conclude, essentially what we did was to devise a 2-time scale stochastic approximation scheme in order to find an optimal n. And then we gave a proof of convergence, and our experimental results show better performance than OCB. Of course, one needs to try more recent algorithms. I think somebody pointed out earlier that in the bandit literature, there are many more algorithms, which of course we haven't looked at. So how it performs in comparison, we still have to figure that out. Yeah, so as future work, one can look at actor critic algorithms, wherein you use an n-step TD critic with an adaptive n and an actor on top of it. Or look at an optimal lambda and TD lambda kind of function, where you use function approximation based schemes. I think I'll stop here and be happy to take it.
So is it known whether the mean square error has some clean functional dependence on n in the first place? For example, is it known to be unimodal or so I know there is a sweet spot.
No, that's interesting. Yeah, it's not, nothing is available. It's just that we observe empirically that it does.
I see. So you seek to find some sort of a local minimum in the n space.
We seek to find a local minimum, but it does better than that. It seems to do better than that, but we don't know. It has to be investigated.
More questions? Let's thank the speaker once again.